Today we're going to look at how we can use integration to find the arc length of a curve. So our goal is to answer questions like this. We have some function f at x, and we'd like to know how long is the curve between a and b. So I want to know what is that length. Right, that's my goal. To find that length right there. And so what I'm going to do is I'm going to go through and develop a formula. In the end, all you have to do is be able to remember and use this formula. You won't have to reproduce all of this this inside stuff, the stuff that we use to get there, although there's some interesting parts to it as well. But let's just get right to developing the formula and then learning how to use the formula to answer the questions that we need. Alright, here's the key point. The key point is that if we start off with some unknown function, some generic function, a and b, what we're going to do is we're going to pretend. Remember that when we integrate, we're adding up an infinite number of really small, tiny pieces. So what we're going to do is we're going to pretend as if this curve, let me get rid of the dark stuff, we're going to pretend as if the curve were a straight line. We're made up of a whole bunch of little straight lines. All right, so if this is f of x, we're going to say, okay, suppose that it were just a straight line here, tiny little straight line, tiny little straight line, all these tiny little straight lines. Straight lines are easy to find the length of. That's just essentially the Pythagorean theorem, right? If I have a straight line, then the length is the square root of a squared plus b squared. So if we pretend that we have a whole bunch of different tiny little straight lines, we can add up all of the lengths of those, and then by turning those straight lines, those tiny little straight lines, even smaller and smaller and smaller, it becomes an infinite sum, which is an integral. So that's the big idea that goes along with this. The way that we get the length of those straight lines, though, that we're using, is essentially by looking at the tangent line. If I have a tangent line to the curve, then I can pretend that the curve is the tangent line on a small portion. So if this is the tangent line, f prime at x, then if the curve is very well approximated by its tangent line for a small region. And so that's what we're going to do. We're going to zoom in right to this spot and say that the curve is the tangent line. Now it's pulled away pretty far here, but if we zoomed in very, very close, we would see almost no difference between the two. So let's look at that. Let's look at what we got. So this is some point. Let's call this point x0. We don't really know what it is. It's some generic point in between a and b. Let's call this delta x. Right, the distance that we move forward along the tangent line. Essentially the length that we're using to approximate the curve by its tangent line. So this will be delta x. If that's delta x, then this is delta y. Right, delta y, the change in the height. So delta y and delta x get us the slope of the tangent line by f prime at x is approximately the rise over the run, right, which is delta y over delta x. So that delta y is f prime at x delta x. Okay, so far so good. Now according to our idea, by using the Pythagorean theorem, what is the length of this piece right in here? The length of this red piece will be the square root of delta x squared plus delta y squared. Right, so that's going to be the length of that small little approximating piece to the curve. And that's fine, right? So that's what we want to do. And then the big picture idea, the calculus idea, is to add up a whole bunch of these. I'm not going to go through all the technical details of what's going on there. Essentially, we end up with a Riemann sum. We have a sum, not an integral yet. We will have a sum of a bunch of different pieces, of a bunch of different lengths here. Square root of delta x squared plus delta y squared. And so this xo, or this x, we should call this, maybe I shouldn't have called that xo, I should have called it x sub I, the ith piece. And then if you remember Riemann sums back from Calc 1, again, this is why I don't want to go through the whole process of getting it, but if you remember the whole development of area under the curve, we had x0, x1, x2, x3. We would make rectangles, add up the area of those rectangles, and then take a limit as the number of those rectangles goes to infinity. And that's exactly what we're going to do right here. We're going to take a limit of these things, of this sum, as it goes to infinity. But before I do so, I want to make a little bit of algebra, which feels a little weird, but you'll see where it leads to in the end. So I want to do some algebra on this whole process. All right. So delta y, I just erased it, but from this piece right here, delta y is f prime at x delta x. So that square root of delta x squared plus delta y squared is square root of delta x squared plus that stuff squared, which is f prime at x delta x squared, all squared, which is square root of delta x squared plus delta x squared times f prime at x squared. And I can factor a delta x squared out of both of these pieces, and I get 1 plus f prime at x squared. Just watch where my parentheses go. The only thing that's squared is the f prime at x. Okay, so good. The square root I can apply to the delta x. So that becomes delta x square root of 1 plus f prime at x squared. So if we go back and look at our sum of a whole bunch of different approximating lengths, that's how you should think about it. This is the sum of a whole bunch of different lengths of these tangent line approximations. And so that will become sum of square root of 1 plus f prime at x squared times delta x. I'm skipping over some of the details with the index. This really is going to be from I equals 0 to n minus 1, where n is the number of subintervals, if you're really worried about those details. In the end, I want to just get to the formula, so I'm hiding some of those. But remember, when I take a limit, when I take the limit as the number of approximating subintervals goes to infinity, the sigma, the sum, becomes an integral. The delta x becomes a dx. This formula stays the same. 1 plus square root of 1 plus f prime at x squared. And this will then go from A to B. And in fact, we're done. This is the formula that we're looking for that will get me the length of a curve between A and B. It's not obvious, right? So when you look at this formula, it's not obvious where it came from, which is why I wanted to go through this process and show you the details. I just want you to remember that really what we did was we took a whole bunch of tiny little subintervals, pretended that the curve was the tangent line, found the length of those tangent lines, since length of lines are easy to calculate, added them all up, took the limit as the number of tangent line approximations goes to infinity, a sum becomes an integral, and this is the formula that we end with. So let me use that formula a few times. Really, in the end, every single question on this comes down to just plugging this formula in and hoping that you can either find an antiderivative if it's a nice function, or else just leaving it as an integral if you can't. So here's our formula. Length is integral from a to b square root of 1 plus f prime at x squared dx. So let's do this with something that's actually we can calculate to convince you that it's true and actually works. Let's look at the following example. This is the circle of radius 1, the upper half circle of radius 1. Remember that comes from x squared plus y squared is 1, so that y is equal to the square root of 1 minus x squared. So this is my function, square root of 1 minus x squared. My question is, what is that length? What is this length? What is the length of that red upper half circle? We can answer that just from geometry, what we know, because we know that the circumference of the circle is 2 pi r. Right? So we know what the answer should be. It should be 2 pi r circumference over 2, right? Because it's just half of the circumference. So it should be 2 pi times r over 2, which is just pi r, but the radius of the circle is 1. So we better end up getting pi back. That's the idea. Right? We better end up getting pi back. Let's see what happens. So if I plug this formula in, if we look at this whole process, what do we have to do? We need to find f prime at x. So f at x is square root of 1 minus x squared. F prime at x is 1 half 1 minus x squared. So remember, this is 1 minus x squared to the 1 half. So the derivative, 1 half comes down, 1 minus x squared to the negative 1 half, all multiplied by the derivative of the inside, which is negative 2x. So the 2's cancel, and I get negative x over the square root of 1 minus x squared. Okay, so far so good. It's just that's just the derivative. All that we do is we find the derivative. When we square it, f prime at x squared, I get negative x squared over 1 minus x squared. The negative actually goes away. So positive x squared over 1 minus x squared. The next part of our formula is adding 1 to it. So if we come up here and we add 1, I will get the integral from a to b. A and b are negative 1 and 1. Negative 1 and 1, so that's the a value and the b value for the limits of the integration. Square root of 1 plus that. Okay, and let's see what happens. Let's do a little algebra. If we do a little algebra, I want to add these two things up. I'm going to turn that into 1 minus x squared over 1 minus x squared so that these two things have a common denominator. So I just turned 1 into 1 minus x squared over 1 minus x squared. Now I can add these two things up. And by doing so, the x squares cancel off and I get the square root of 1 over 1 minus x squared. And we end up with this integral. Then we have to go back and remember some of our antiderivatives or derivatives. This one is a little bit of an odd one. We'll see it a bunch later on when we get to chapter 7. But you may recognize it as an inverse trig function. This actually leads us to sine inverse. So hopefully in Calc 1 you talked about the derivative of the inverse trig functions, and the derivative of sine inverse is 1 over 1 minus x squared. So the antiderivative of this is sine inverse of x, evaluated from minus 1 to 1, which is sine inverse of 1 minus sine inverse of minus 1. Sine is the y value. What y value, what angle on the unit circle has a y value of 1? Well, the angle on the unit circle that has a y value is up here. What angle is this? This is pi over 2. So that's pi over 2. What angle gets a y value of -1? Well, -1 is right here for y value. The angle that leads me to this is negative pi over 2. So this is minus negative pi over 2. I get pi over 2 minus negative pi over 2, which is exactly pi, as we pointed out at the beginning, it ought to be. So I hope that that convinces you that the formula works. And it does. This formula does work. Most of the time, it's not going to work out nicely. If you look at this formula and I give you a function and say take its derivative, square it, add 1 and then put it under a square root, odds are you're not going to be able to find an antiderivative. And that's okay. If it's a messy function, what I'll only ask you to do is set up the integral that gets you the length. Most of the time that's the best that we can do with these things. That's really all there is to it. Take your function, find the limits of integration, take its derivative and put it into this formula. Alright, see you next time.